Hey there, chemists. It's Dr. O'Malley here, and today we're going to talk about bonds, specifically bond lengths, bond energies, and also wrap it up with topics related called hybridization and resonance. So the first thing I have on your screen is an animation that shows two atoms, one of them pinned and the other one at some distance away, distance that it's far enough that there's actually no potential energy between the two. And that's what this graph shows. It shows how far the atoms are and what kind of energy is going to result from the distance between those. So if I actually start the animation, I can slowly bring this atom toward the other one, and we'll see that there's an attractive force that brings them together. That's because the protons of one are attracting the electrons with the other, and vice versa. But there's also repulsive forces between the two. As they get close to each other, we have an unfavorable repulsion. Whoa, I can have it fall all the way away. Where you end up in this upper region of the graph because it's such a high energy state. But then there's an optimal distance where the two atoms are near each other and the attractive forces are balanced with the repulsive forces. So let's look at our notes. This is exactly what you have on your notes. If you flip back to the lesson 8, I think we're on, in the upper right corner, there's a picture of this graph. And if we take a look at this graph, I see two atoms that are very, very far apart. I'll actually write too far, where I have zero energy between them. And then I have two atoms that are really, really close to each other, so I'll say too close, where the repulsive forces are actually causing a unfavorable high energy state. But then down below, you see in this trough, you have an optimal distance. And that is a graphical representation of the bond length, how far the atoms are from each other so that there's a balance between the repulsive and attractive forces. It also graphically shows us the bond energy, which is something we're going to look at later on in the semester, but it's worth pointing out here in the meantime. So off to the left, there's a chart that shows various bonds between a number of different nonmetals, and I want you to look at the different bond lengths and see if you can come up with at least one trend that seems to generalize what we observe about bond lengths. So hit pause and look for something that you can generalize about the types of bonds and the different types of elements that form bonds. Okay, hopefully looking at this you came up with at least one thing. There's actually two I want to write down. And hopefully you came up with at least one of these. The first one is that smaller atoms form shorter bonds. And I can see that if I compare, let's say, the bond between two fluorine atoms with the bond between two bromine atoms. The larger bromine atoms form a longer bond than the smaller fluorine atoms. Secondly, if you look at the different types of multiple bonds between the same types of atoms, as we go from, let's say, the carbon-carbon single to the carbon-carbon double, and eventually the carbon-carbon triple, it gets shorter and shorter. So triple and double bonds are shorter than single bonds. The atoms are sharing more pairs of electrons. They are closer to each other. They also result in a stronger bond, which we'll get to when we talk about bond energies later on. So just to make sure we've got this, if I compare the pairs in this question number 45, which bond in each pair is longer, it's asking for. Well, the double bond is going to have those carbon atoms further from each other than the triple bond. So based on the second generalization we wrote over here, I think the first one is the answer to choice A. For B, we have a carbon-sulfur bond versus a carbon-oxygen bond, so they're both with carbon, and we want the one that's longer, so that must mean we're looking for the atom that's larger. So sulfur versus oxygen, it's going to be the carbon-sulfur bond that's longer in this case. Likewise, for choice C, the sulfur-sulfur bond should be longer than the oxygen-oxygen bond, because sulfur has a larger atomic radius. So just a couple of simple trends to look at with bonds based on our periodic table trends and results in what kinds of lengths we see. Now the second thing I want to talk about today has to do with orbitals. So we're going to take a step back and look at orbital diagrams. Remember, we drew these orbital diagrams in the past. They're a way of representing electron configuration. And when atoms form bonds, they sometimes hybridize their orbitals to exhibit more favorable geometries. And we see this primarily with carbon. That's the most common example that comes up. And there are three types of hybridizations to know. And they actually correlate with the three most common geometries that we see with carbon, and they show them down here. Before I actually have you write anything down in your notes, let's take a look at a quick animation that shows what happens. So here's a single s orbital and three p orbitals, which is exactly what we have in a carbon atom, in its valence at least. We have 2 electrons in the s orbital and 2 electrons in the p orbital. So we have a total of 4 orbitals in the valence shell in the second principal quantum energy level. And they can hybridize with each other. So if we do that, we'll have 3 p orbitals and 1 s orbital come together, and they'll make 4 equivalent, what are called sp3 hybrid orbitals. And this exhibits a tetrahedral geometry with the bond angle that we saw last week, 109.5 degrees. There are 2 other hybridizations that are worth knowing. The sp2 hybridization involves only 2 p orbitals and a single s. They come together to make 3 equivalent sp2 hybrid orbitals, and that exhibits a trigonal planar geometry with a 120 degree bond angle. And lastly, the sp hybridization only uses 1 of those p orbitals and 1 of the s orbitals, and you get 2 equivalent hybrid sp orbitals. The name simply comes from how many of each type of orbital that goes in there. There are 2 others that incorporate d orbitals. We can look at them just for fun. We see these with expanded octets. This is called an sp3d because 3 p's, an s, and 1 d orbital come together to make 5 equivalent hybrid orbitals. That goes with a trigonal bipyramidal geometry. And lastly, the sp3d2 system brings in 2 d orbitals, and you get 6 equivalent orbitals with an octahedral geometry. And this link just summarizes those 5 types of hybridizations. Now, it's really only the first 3 that we're going to see more often than anything else, but you notice all 5 exist and they match up with the 5 electron geometries: linear, trig planar, tetrahedral, trig bipyramidal, and octahedral. Those go hand in hand with hybridizations. So if we know the geometry, we can predict the expected hybridization. Okay, so let's recap a little bit of that on your notes. And if we draw what happens, well, the 4 hybrid orbitals in the valence shell hybridize and combine to give you 4 equivalent hybrid orbitals, which I'm just going to draw as lines like any other atomic orbital diagram. And each one has 1 unpaired electron in it. This is what happens when carbon actually forms bonds, in this case with hydrogen atoms in this ethane molecule down here. And it's a good explanation for why the carbon's valence electrons form 4 equivalent bonds in a nice tetrahedral geometry. But we know that carbon can also make only 3 bonds if 2 of them are single, and 1 of them is a double. In this case, you have 3 equivalent sp2 orbitals with 1 electron each, and you still have 1 unhybridized p orbital with a single electron in it. So only 3 of these 4 valence orbitals have hybridized in the sp2 case. And lastly, with the sp case, we have only 2 hybrid orbitals classified as sp with 1 electron each. And then there are 2 remaining unpaired electrons in unhybridized p orbitals. So we took only 1 of these p orbitals, merged it with the 2s, and you get an sp system. That's why it's called sp, because there's 1 of each that hybridize to make this. And then the other 2 p orbitals are still there, and they're in a slightly higher energy state. And this actually explains the different types of bonding that we see, particularly around carbon. And we can classify the types of bonds by using this orbital notation. And let's actually take a closer look at one of them. Here's a closer look at the middle one, the ethene molecule. And if we remind ourselves what hybridization we have, it says right there, it's sp2. So we'd have 3 sp2 orbitals and 1 p orbital, and that would be the same for the other carbon atom as well. The hydrogens that it's forming bonds with, well, each of those just has 1 electron in the s orbital, the 1s electron, and all 4 of those hydrogens are the same. So these actually show what electrons make up these covalent bonds in a slightly bigger molecule than some of the ones we looked at last week. The pi bond is what we call the carbon-carbon bond that's made from the 2 p electrons. And there's a little blurb over here that reminds us of that. A pi bond involves orbitals overlapping above and below the axis connecting atoms, and this occurs between 2 p orbital electrons, and that's the pi bond. The sigma bond is pretty much everything else in this case, and sigma bonds happen anytime you have an overlap between hybrid orbitals or s orbitals. So these 2 sp2 electrons are overlapping to make this sigma bond, and the other 2 on each carbon are overlapping with all the hydrogen 1s electrons to make more sigma bonds. So we can describe what types of orbitals are involved in making each of these bonds. It's not too important to know all this detail. What's really key here is that the sigma bond is a stronger bond than the pi bond, but obviously the 2 combined are stronger than just either one. Okay, so let's go back to our notes, and then there's only one more thing to talk about, and that has to do with resonance structures. Now, resonance structures is a way of describing more than one correct Lewis structure for a given formula. It has to do with the fact that not all the electrons are shared evenly by 2 atoms. They might actually be delocalized, in other words, shared by more than just 2 atoms. So sometimes drawing a simple Lewis structure picture for a molecule isn't sufficient, and you'll know you have valid resonance contributors if all you've done is change the placement of electrons. So let's actually make a note of that. Resonance structures in resonance electrons are distributed differently. I'm actually going to say only electrons are distributed differently, which means that the atoms are still connected in the same order, but we have a different placement of electrons. For example, in the nitrous oxide example, this came up in the molecular modeling activity. Nitrous oxide is N2O. If I count my total valence, each nitrogen has 5, so 2 times 5 is 10, plus 6 for the oxygen, so I should have 16 electrons. And one valid structure, starting with an N connected to an N, and then an oxygen, looks like that as a skeletal. Now, if I distribute my electrons everywhere to satisfy the octet, the nitrogen would need 6, the middle nitrogen would need 4, and the outer nitrogen would also need 6. But if I count my total here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, I've used 20 and I only have 16. So since I'm off by 4, I need to have 2 extra bonds. So if I take away a pair from each nitrogen and make them share 1, and then I'll take a pair from another, the other nitrogen and an oxygen and make them share a pair, then I get a structure that looks like that. And that works. But this is not the only valid structure. We can also draw a nitrogen connected to a nitrogen and connected to an oxygen, but the sharing can look differently. Instead of 2 double bonds, we could have 1 triple and 1 single and have the same electron count and still satisfy the octet everywhere. So if I put a triple bond between the nitrogens and then satisfy the octet on the nitrogen on the left and then satisfy the octet on the oxygen on the right, you actually get a perfectly valid structure. These 2 structures are resonance hybrids of each other, and we denote that by drawing this double-headed arrow in between the 2. They are the same connectivity. The only thing that's different is the distribution of electrons. Only electrons are distributed differently. And this isn't even the last one. There's actually yet another with the same connectivity, and this time you could have a triple bond between the nitrogen and the oxygen. And then if I satisfy the octet on every other atom, you get a valid structure with the triple bond between the N and the O. So all 3 of these are actually different representations of one molecule. The true structure of nitrous oxide looks like something in between all three of these. Now, for the purposes of this course, all that's important is to know how to recognize when two structures are just resonance. And the key is just that the only thing that's different is the electrons. The placement of the total number is the same, and the connectivity of the atoms, the order in which the atoms are bonded to each other is the same. So let's look at a few other examples. Ozone, remember what ozone is? That's O3, a very important molecule in the upper layers of the atmosphere. Very dangerous at lower levels of the atmosphere, but very important in upper levels of the atmosphere. It absorbs ultraviolet radiation. Ozone is 3 oxygens connected in a series. There's a double bond between 2 of them, and then if I distribute my electrons to satisfy the octet, I use all 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons, and that's exactly how many I have to work with. Now, if I draw the structure like this, it looks like there's an isolated double bond between the first 2 oxygens and an isolated single bond between the second 2 oxygens, and that's simply not the case. It also exhibits character where the first 2 oxygens have a single bond and the second 2 have a double bond, and in fact, the true structure looks like something in between these two, as if these 2 electrons that form the pi bond are sometimes over here and sometimes over here, and the true structure is actually a hybrid of the 2. The most classic example of resonance is benzene, and I have that drawn in the lower left here. I don't like to start with benzene because the 2 resonance contributors look identical to each other. It simply looks like it's been flipped around, but they are actually different representations of the same molecule. For example, if I just highlight these 2 carbons, they currently have a single bond between them, and over here they now have a double bond in between them, and the true structure is a hybrid in between. And just for one more example, maybe hit pause, try the last one, see if you could come up with one valid Lewis structure for this, and then we'll see if we could come up with a second one for that too. Okay, so let's see how we did it. The formula here shows me a little bit about how it's built. It's carbon with 2 hydrogens and then 2 nitrogens. So I have a carbon, it will be connected to 2 hydrogen atoms, a nitrogen, and then another nitrogen. And one valid structure has double bonds between all the atoms except for carbons, and then I have lone pairs of electrons on the nitrogen on the end here. An alternative structure would have a single bond between the carbon and the nitrogen and a triple bond between the 2 nitrogen atoms. That would result in a lone pair on the carbon atom and one more lone pair on that distal nitrogen off to the right. So these structures look quite different, but only because the placement of electrons is distributed differently. That's what resonance is all about. Okay, so that covers how to draw resonance structures, a little bit about hybrid orbitals, and then some very easy stuff, I hope, about different bond lengths. So in class, we're going to go over the problems on the back. Thanks for watching.